So first, I just want to take you through a few introductory concepts about chemistry in the class as it stands as a general science class throughout the year. A couple main ideas that sort of apply to chemistry certainly, but to all science classes that you might take here and after, and hopefully all science classes you've had before now. First of all, quick definition of chemistry. Generally, we would define chemistry as the study of structure and properties of matter. Pretty straightforward. Those are just a few words that encompass the whole year, essentially. And hopefully at any point in the year, you'll see that anything we're doing falls under that simple heading, the study of the structure and properties of matter. We'll start with structure, how an atom is built, how we figured out how an atom looks and is built, or at least how we think we know it to be today. And then sort of as we build throughout the year, we'll be alternating in combinations of the structure of matter, how atoms are put together, in different molecules and compounds, the bonds that are formed, and the properties that come about as a result, including the reactions that can and can't happen between different kinds of compounds. The scientific method is sort of the backbone for all science classes, for all science study at all, whether you're in a class or just kind of observing your world. You should be able to see, if you're looking at it critically with an eye on science, that lots of things you do every day and lots of everyday actions have their sort of root in the scientific method. It starts out with just sort of a simple curiosity, and people are very curious by nature. This is why we do crazy things like go to the bottom of the ocean and go to the moon or go to Mars or send probes into the universe to see what we can find out about our world and our universe. We're curious people, and with big brains, we're sort of asked, or I guess challenged, to go out and figure things out about our world. That's why we look at things smaller and smaller, microscopes, and try to look at small cells and atoms or huge things like the universe. So in any beginning of science, we should find a curiosity or a question. And the scientific method is sort of at the root of all that. The first sort of stage of the scientific method is sort of grouped as something called observations. You're simply looking around, seeing something that you don't understand, not knowing what's going on in the world and wanting to figure out why something's happening, or wondering what would happen if. What if I did this? What would happen? Of course, you want to do all those things safely, and hopefully you'll conduct experiments safely, certainly in chemistry class, but even if you're sort of an everyday scientist trying to figure things out in your world. But you see something that you're curious about, and it forms a question in your head. You might do a little research with it. You might not even realize it. The word research shouldn't necessarily mean going to read through books or journals or going online to try to learn more, although it often means those things. Sometimes research just means sort of thinking about what you already know, considering what do I know about why that happens and what don't I know? What have I heard before? Sometimes you'll find out that your research will later on be proven to be somewhat false. Maybe you had bad misconceptions, or someone taught you something poorly, or you learned something once, or you heard it once and you didn't soak it up quite right, so you've always sort of misunderstood. Lots of good examples of that. But observations will begin with you seeing something, kind of puzzling about it, and then sort of forming a question. Why does this happen, or what would happen if? After you've done a little bit of research, you form a hypothesis. And a hypothesis is sort of a statement of fact. You may not form a question here necessarily, but you want to make a statement. It shouldn't have a question mark at the end. It's often a mistake people make with hypotheses. It shouldn't be a, what will happen if I do this? It should be, I believe that this will happen. Or just simply, if I do this, this will change. It's not necessarily a question because at this point you're trying to make a statement that you'll later prove to be either correct or not. You'll either confirm or reject your hypothesis. So you're not answering a question in your hypothesis, you're sort of writing the answer to your question. Whether it's right or wrong will be proven later. And then you construct an experiment. Now there's lots to doing that, and we'll talk a lot about constructing experiments. We'll talk about variables, how we set up an experiment with independent and dependent variables, keep those things sort of planned out in advance. And you want to, with an experiment, hopefully not just dive right in and start mixing things or heating things or doing stuff without planning a little bit. Reason being, as much as it's fun to just start lighting things on fire in a lab or mixing chemicals together, you need to know about safety. You need to know what kind of containers you might need as you go through so you're not caught without what you need. It's just like planning. If you're planning to bake something, you want to get all your ingredients together and make sure you've got things together. Otherwise, you get halfway through mixing things and you realize you don't have what you need and you'll have to run to the store. In the chemistry lab, a lot of reactions, you'd miss something if you had to run over here and pick up something you'd forgotten. So you want to think ahead, you want to plan ahead, you want to have all that you need together, and you want to be in the lab especially safe. And so experimenting means planning it out well and having a good plan before you ever begin, sort of seeing the end or beginning with the end in mind and working your way toward that. Doesn't mean you can't sort of adjust on the fly a little bit. We almost always have to do that. But you should certainly start out with a plan that's not just we'll just see what happens and try it as we go. That often leads to YouTube videos where people are getting hurt, all sorts of examples. We don't want to have that happen in class. As you're doing an experiment, you see here you want to keep your observations rather organized, things you see as you're doing your lab, whether it's making a measurement of something, a temperature, a volume, a mass. You want to make sure those things are written down neatly and not just a bunch of messy chicken scratch. And you always want to write down more observations than you might ever think you'll need. This isn't just numbers, but just, this changed color, or this got warm, or this started to bubble. Even if you think, obviously it was going to do that, or that's not important, you should always write those observations down, because you can always get rid of the stuff you didn't need, not include it later in your report, but you can't go back and get those things back. Once you've missed them, they're here and gone, and you should be recording those things in great detail. This is why a lot of experiments and things are done by video. When you're doing a new experiment, you might set up a camera to record things. I see this in movies and this sort of thing where they have cameras on the reactions, or animal experiments where they're recording it by video so they don't have to worry about missing as much. And then conclusions at the end. This includes an important stage that's not really mentioned here by name, but that's analysis. You want to make sure that you're doing some analysis of your results. Go through and see, does my data support my hypothesis? I said that if I heated this, then the reaction would change in this way. Is that what happened? I said that if we adjusted the height of the ramp on our race car, that the race car would fly further. Did that happen? You want to do some analysis, compare your results to what you believed would happen, and see what turns out to be true or false. And it's certainly okay to be wrong. In fact, most of the time your hypothesis turns out to be false. It's more fun that way, because then you get to construct a new hypothesis and do it again. Further experimentation, it says here, is necessary, almost always is necessary. Even if you were right, it doesn't mean you're done. You're going to go back and probably do your experiment several times, many times over. Go back to the beginning of whatever method you put together and start again. A great example of this is in medical pharmaceutical experiments. They design a new drug that's going to help cure cancer or something. You're not going to test that drug on one person, and if it helps them, then just assume it's going to help everyone. Any kind of a drug, whether it's a drug to help you stop smoking, or something to help cure cancer, or something to cure baldness, or who knows what it is. You're not going to test that on one person and call it good. You're going to test that on many people, because one person's reactions and side effects might not be the same as everyone else's. One person's not good enough. Test it on many people. Test it on many people safely through very, very scientific methods. And then at the end, if you've got good enough results, the FDA or whatever agency is governing your experiment and the results of your drug trying to be sold off to the public can look at it and say, yes, you've done your due diligence, you've looked at enough experimental results, and now you can be confident that your drug is safe for the public to use. They're not going to let you send it out to the world and sell it. If you tested it on one person, your guinea pig of an uncle who was fine with you testing it on him, and now you're off to the races and you're going to sell it to the public and hope that it works for them. So an experiment almost always needs many, many repetitions in order to give you a solid, confident result. In lab, we won't do things many times, but we'll do things, at least in most experiments, we'll do things 2, maybe 3 times to try to prove that it wasn't a fluke, whether it was a bad fluke or a good fluke. I'm also adding a link on the bottom of the screen here to a video, and I'll also include a link there on the YouTube page that will take you to a video of a song called Put It to the Test by They Might Be Giants. If you've never listened to They Might Be Giants before, they're definitely an odd group. They have a way of putting ideas into songs that are very unusual, and they have a whole album actually devoted to science-related songs. And the one called Put It to the Test is all about the experimental method, essentially the scientific method of setting up an experiment, how you think about a problem and how you ask a question and how you put it to the test. So it's a great song, cool video. It's a kind of a throwback-looking sort of retro video that looks like a 1980s video game in its pixelation, but it's a pretty sweet song. And if you take a look at it, it'll maybe help you to understand some of the relationships, and it's one of those very catchy tunes that They Might Be Giants does. So hope you enjoy it if you get a chance to watch it, and maybe I'll play it for you in class too. That's it for now. We'll be back later with variables, things that you adjust and keep the same in an experiment, and talk more about how each of those is important both for your experiment and for the analysis of your experiment.